Okay, picture this. You've got this massive biological dam inside your body. Its entire purpose is to meticulously control the flow of water, opening and closing gates based on exactly how much hydration you need at any given second. But suddenly, out of nowhere, those gates are jammed wide open. The signals are totally broken, and water is relentlessly backing up into the system. What happens to the floodwaters? Where do they go? And how does your body try to survive the deluge?
Welcome to this explainer on SIADH, or the Syndrome of Inappropriate Antidiuresis. Today, we're taking a masterclass in how a single microscopic glitch can trigger a massive systemic flood. We're going to dive deep into the exact mechanics of human physiology, tracing the path of water in the body, the cellular receptors that trap it, and the absolute high-stakes consequences for the human brain.
Section 1. The Vasopressin System Baseline. All right, let's set the stage. To really understand how our biological dam breaks, we first need to look at how it operates under normal, healthy conditions. Up here in the Master Control Center for water, the normal brain-kidney axis is at work. In the hypothalamus, the body produces this tiny vital hormone called Arginine Vasopressin, or AVP. This AVP is your ultimate gatekeeper for water. Once it's produced, it gets processed in these neurosecretory vesicles, and then it's transported all the way down the axons to the posterior pituitary gland, where it just sits and waits for the signal to be released.
And that release signal relies on a very specific number, 275. You see, osmoreceptors in the anterior medial hypothalamus are incredibly sensitive. They can detect even a tiny 2 to 4% change in sodium. 275 milliosmoles per liter is the crucial plasma osmolality threshold. When your blood is dilute, meaning osmolality is below 275, AVP is firmly suppressed. The gates are closed, and you naturally excrete water. But the second it rises above that threshold, telling the body your blood is getting a bit too concentrated, AVP release spikes steeply. It's a remarkably elegant, highly calibrated system.
Section 2. Defining inappropriate antidiuresis. So, what happens when it breaks?
Well, what happens when that careful calibration is completely lost? That brings us to the formal definition of the Syndrome of Inappropriate Antidiuresis, or SIAH. At its absolute core, it's the inappropriate elevation of AVP. The body is relentlessly releasing this water-retaining hormone despite the fact that the blood is already hypotonic and the patient is euvolemic. Basically, the osmolality is low, AVP should definitely be suppressed, but instead it's just firing continuously. This non-stop water retention dilutes the blood, inevitably leading to hyponatremia, which is a serum sodium level falling below 135 milliequivalents per liter. The body is hoarding water when it literally has no business doing so.
Section 3. V2 receptors and aquaporins. Let's zoom in a little closer.
To understand exactly how this hoarding happens, we have to look down at the microscopic level, right inside the kidney. This inappropriate AVP travels to the kidneys and binds to highly specific targets called V2 receptors. Activating those receptors triggers this whole intracellular cascade, stepping up cyclic AMP levels. That surge in cAMP acts as a definitive command, literally forcing water channels, known as aquaporin 2 or AQP2, to be inserted directly into the lining of the kidney's collecting ducts.
And because these aquaporin channels are forced wide open by that rogue vasopressin, relentless excessive water reabsorption begins. The kidneys essentially lose their ability to dilute urine. Even though the plasma osmolality is already dangerously low, the persistent action of AVP just continuously pulls free water right back out of the urine and straight into the bloodstream.
Section 4. The euvolemia paradox. This is where things get really fascinating.
Let's zoom back out and address this massive systemic mystery that all this water retention creates. Just think about the physics for a second. If those V2 receptors are constantly activated and the kidneys are endlessly pulling free water back into the blood, why doesn't the patient just balloon up? Why aren't they presenting with massive noticeable swelling all over their body?
Intuitively, you'd totally expect massive systemic edema, kind of like what you'd see in severe heart failure, right? But the actual clinical presentation of SIADH is just modest extracellular fluid volume expansion. In fact, these patients generally appear euvolemic, meaning their fluid volume looks pretty much normal from the outside. So, where on earth is the body hiding the floodwaters? Well, here is the systemic adaptation. As that initial retained water slightly expands the extracellular fluid, the body detects this pressure, panics about fluid overload, and triggers something called pressure natriuresis, while simultaneously reducing aldosterone. Basically, it forces the kidneys to dump sodium into the urine, which pulls water out with it to maintain a normal volume. It successfully prevents massive swelling, keeping the patient euvolemic, but there's a devastating cost here. By dumping sodium to save the fluid volume, the body actively makes the underlying hyponatremia even worse.
Section 5. Causes and clinical triggers. Let's look at what trips the wire. So what's actually causing this wildly inappropriate AVP release in the first place? When we look at the systemic triggers, we find an incredible, truly diverse array of culprits hijacking the posterior pituitary. SIADH is rarely just an isolated problem with the pituitary itself. It's more like the pituitary is being manipulated by external crises. It's this single mechanical failure point being driven by a multitude of systemic diseases. Looking at the data, the culprits are remarkably widespread. Malignancies are a huge trigger, particularly small cell lung cancer, which is wild because it can actually produce AVP all on its own. Then you've got central nervous system disorders like meningitis or a stroke, and pulmonary infections like pneumonia. Even everyday medical treatments can trigger it. Common drugs like SSRI, antidepressants, carbamazepine, and NSAIDs can actually enhance the release or action of AVP. And, in some rare instances, hereditary gain-of-function mutations directly in the V2 receptors can cause a nephrogenic version of the syndrome.
Section 6. Brain adaptations and edema. Now for the real danger zone.
As we've seen, the causes are incredibly diverse, but the end result is always severe water imbalance. While the patient appears to have a normal fluid volume on the outside, internally, the physics are completely treacherous. You have this dangerous increase in total body water relative to total body sodium. The blood has become profoundly hypotonic. It is quite literally too watery.
And nature absolutely abhors an osmotic imbalance. Because the blood is dilute and hypotonic, water naturally flows via osmosis right out of the bloodstream and directly into the more concentrated cells of the body. Now, when this water rushes into the cells of the brain, those cells swell up. But remember, the brain is trapped inside a rigid, unforgiving bone vault, your skull. So this acute hypotonicity triggers severe cerebral edema.
This brings us to a crucial point. SIADH isn't just some interesting kidney or endocrine anomaly. It is a profound neurological emergency. When the brain swells, the symptoms directly reflect that swelling tissue. Patients present with severe headaches, altered mental states, confusion, and if that drop in sodium is acute and severe, it can quickly escalate to seizures and massive morbidity.
So, the biological dam has broken. The body essentially dumped its own sodium just to prevent flooding, and now the brain is swelling from the resulting imbalance. It's an absolutely stunning cascade of physiological dominoes, and it leaves us with a terrifying clinical dilemma. We know that if we forcefully correct the sodium imbalance too quickly, the sudden osmotic shift can literally strip the myelin right off the brainstem, causing locked-in syndrome. So if fixing the problem too fast is just as dangerous as the disease itself, how do we safely coax that jam dam closed? That is a precarious tightrope of clinical management that we'll have to leave for you to ponder. Thanks for joining me on this explainer. I hope you found it as fascinating as I do.